Good morning and welcome to the LIPS final workshop. I hope everybody can hear me well. My name is Jens Pilz and I'm working for Sennheiser. I will be your moderator for today. This final workshop was originally planned as an on-site event. Due to the pandemic situation, we had to reorganize and adapt accordingly. Although the true benefit would be to experience the project results live here at Sennheiser HQ or in Munich at the university. We hope to give all the participants and viewers out there a good impression of what it is like to use the LIPS technology and the setup developed in the project. We stream live via YouTube, and thus there's a delay between our production and distribution. You can ask questions after each talk via chat or email. The email address is questions@lips-project.de as shown below. Please take the delay into account. So I would advise to just write the question during the talk. This gives me time to collect and ask your questions directly afterwards. And now we're switching live to Munich to give the stage to Professor Dr. Bernd Redmann, President of the University of Music and Performance Arts, Munich. Hello, Professor Redmann. Okay. I can see he is not in the room at the moment. So, there he is.
Good morning.
Hello, good morning.
Dear ladies and gentlemen, wherever you are, welcome to this final workshop of the LIPS project here from the main building of the University of Music and Performing Arts in Munich. As president of the university, I'm excited about the research results of LIPS, and I'm pleased that my university is part of this forward-looking project. I'd like to thank to our cooperation partners, Sennheiser and ARI, and the University of Music, Performing Arts and Media in Hanover. Communication with low latency in music became a highly topical issue due to the corona crisis. In recent months, a real race for innovative technological solutions has broken out here. The LIPS project started long before corona. The good and intensive preparations laid the foundation for the outstanding results that now have been achieved. My university is planning to open a new digital art center in autumn 2021. In the next few weeks, we'll open the new Wave Lab Center as an incubator for cultural and creative industries. It would be great if, inspired by the LIPS projects, we could continue successful cooperation, and if we could explore perspectives for further cooperation, technological cooperation in building up these centers. Finally, I'd like to thank the musicians. I'm looking forward to the concert we are going to listen to, and I wish you all a interesting and insightful Friday morning. Thanks.
Thank you. Thank you, Professor Redmann. This was live from Munich. And now we get a more detailed overview of the LIPS project from my colleague, Dr. Axel Schmidt. Axel, there you are. Good morning.
Yeah. Good morning, Jens. Thank you very much for the introduction.
Yeah, so the stage is yours.
The stage is mine? Okay, so good morning, everybody out there. So I have now the pleasure to give you a short overview of the LIPS project. LIPS stands for Live Interactive PMSE Services. What does this mean? So live, of course, I think it's clear. It's the experience of the artist or for the artist and the audience. Interactive means we want to connect events, not only distributing, but having interaction between all sides and the audience, maybe. PMSE, this is a short of program making and special events. Nobody knows what this means, but this is an summarizing of all wireless applications for professional audio and video production. For example, microphones, so wireless microphones, cameras, and light and sound control, for example. And services, yes, we want to develop new tools that makes all the 3 topics above feasible. What are our goals and our motivation for that? So we want to enable future network activities, even today. So we want to enable remote audio and video production for the future. Very, very interesting and important fields. And of course, this immersive conferencing becomes more and more important nowadays. Even the remote participation in cultural events is very important for us, and this network music making, where we come later to this, because this is the focus of today. The solution we plan, so we want to overcome the spatial boundaries caused by, for example, geographical situations like the rural areas, or what's actual today caused by social restrictions. Our approach here, so on the one hand, we build up a benchmark test with currently available network technology. This is what we will see later on. So we here focus on this network music performance. That's the reason why we connect both stations, so both sides, this side here and the other side in Munich. There we have an integration of audio, white and light, of audio, video and light to create a kind of immersive user experience for the musicians on site. One topic of that is the optimization of the overall latency to make this virtual rehearsal possible at the end. The other bench of our approach is the exploration of future network technologies. Here we are looking at 5G, maybe 5G works as an enabler for new audio services in the future. And later on, you will hear a lot of talks or interesting talks about both topics more in detail. Our consortium is diverse, let's say that way. On the right side, you see the academic partners. We have 2 universities. It's the Leibniz University of Hanover. They focus on all kind of audio processing and the immersive audio stuff. Then we have the Friedrich Alexander University of Erlangen-Nürnberg. Their part is the synchronization. And we have the academic research of the Heinrich Hertz Institute. They are experts of 4G and 5G. On the left side, you see the industrial partners, starting with Smart Mobile Labs. On the bottom, they are experts of all kind of networks. Then, of course, we have ARI, the big experts of all kind of video PMSE and light. The well-known TVN group as a kind of PMSE user, and of course Sennheiser as expert of audio, and of course we have the lead of that project. A short outline of the project. So it runs more or less 30 months, sorry. The overall costs are roughly 6.5 million, and 3.8 million are funded by the Federal Ministry for Economic Affairs and Energy. 7 project partners, as mentioned before, and we have 11 associated partners. You see the list there, very famous and well-known partners of industry. And I think that's for me. Thank you very much for your attention. And I will hand it back to Jens.
Thank you, Axel. So, as I understood, the LIPS project is about enabling future network activities for PMSE. Connecting rural areas with cities to overcome the digital divide is especially important in today's circumstances. Originally, the project wasn't planned with a global pandemic in mind, but becomes a new relevance under the current global events. Connecting virtually become a widely adopted technology in almost no time. The technology available today is good enough for private calls. Professionals in the creative and culture industry have more stringent requirements for their need. So to elaborate on that, we switched to our next speaker. It's Robert Hübke from the Leibniz University of Hannover. Robert, hi.
Hi, hello Jens.
So you give us a talk.
I'm fine. I'm happy to be here, and if I allowed to start, I can start.
Yeah, go ahead. The stage is yours.
Thank you, Jens. So also from my side, a warm welcome. My name is Robert Hupke. I'm a research assistant at the Institute of Communications Technology of the Leibniz University in Hanover. And in this presentation, I will provide you an introduction on the challenges and key aspects of network music performances. So in particular, I refer to the use of the internet or a computer network where two or more musicians are connected to make music together. So such a system is a very useful tool when we cannot meet each other physically for different reasons. For example, of long distances, a large amount of equipment, maybe traveling costs, and especially in these times when you cannot leave your home for any reason. So this presentation is divided into 3 sections. First, I will give you a short introduction to network music performances in the context of network music systems. In the second section, I will talk about the challenges and requirements from the more music technology perspective, and then I will focus on some network performance parameters. And in the third section, I will go a little bit deeper into the topic of synchronization, on the impact of latency and how to cope with latency. So network-based music applications can be classified by different categorizations. What we see here is a diagram by Barbosa back in 2003. So the applications are classified based on their location and on interaction. So we can make music together co-located in the same physical space, or we can make music together at remote locations. In terms of interaction, which relates to time, we can play music together at the same time synchronously, or we can work on music on different times asynchronously. So network music performances are the applications with the greatest technical challenge, playing music together at the same location synchronously. But what is a network music performance? So in music performances, we usually have a large number of different participants. So we have musicians or other performers. We may have a conductor. We have sound engineers, light engineers, or VD engineers. And of course, we have the audience. And depending on the event, all these participants are co-located in the same physical space where they can interact together. So the idea of a network music performance is to distribute and interconnect all these participants in different geographic locations so that each participant corresponds to a network node or a node in the network. So the physical space becomes a virtual one, a so-called virtual remote environment. And in this virtual environment, the participants have to interact. So in order to provide a high-quality interactive experience within the ecosystem, a realistic performance condition must be ensured inside this immersive virtual environment, because just this allows musicians at geographic different locations to perform and interact with each other as if they were in the same space. Of course, such a system might not only be used for concerts, but there might be also other applications like rehearsals, online teaching, musical teaching, maybe also school teaching, jam sessions, and of course, many more applications are conceivable. So now let's take a look on the requirements and challenges which are needed to play music together within a remote network performance. So if we play music together in the same room, we rely on several modalities in addition to the sound generated by our own instrument. So first, as I said, we have the sound of our own instrument. But of course, we need also to hear the sound of the other musicians which are playing. Through sound reverberation, we can achieve some kind of immersive feeling. We get a feeling about the room conditions, and we may get an idea about where the instruments are located within the environment, especially if we are playing together with more than 2 instruments. This corresponds to some kind of virtual acoustic environment which is needed within our network music performance. And of course, we need some kind of visual feedback. to understand what happened on the remote location. So even for simple things such as the coordination at the beginning of a performance, a visual feedback is just as important as the auditory feedback. This can be achieved by some kind of immersive video recording and playback, or maybe by some virtual visual environment where we need to use mocap systems to track the positions and the movements of the participants. And there's the problem of distance. So distance corresponds in a network music performance to latency. But I think you can imagine that if you're standing 100 meters far away from each other and you don't have a conductor in the middle of it, so it becomes quite difficult to play together or interact together. So we need to reduce latencies, or if this is not possible, we have to use some delay compensation strategies. So these requirements of musical interaction can somehow be translated into some very challenging requirements in respect to the network. So we have the audio and video quality, which corresponds to bandwidth, which is a measure of actual amount of data sent over a network per unit of time. Delay and synchronization corresponds to latency, which is the time for a data packet to reach from sender to receiver, hopefully measured in milliseconds. And there might be an additional delay, which is caused or can be caused by some network jitter, which is the probabilistic variation of latency. But the delay is not only caused by the propagation path of the network. So here we can see an exemplary signal path of an audio signal. It's called the overall one-way source-to-ear delay. And it's a simplified path. The sound needs to travel from sound source generation to the ear of the remote musician. So the dark blue colors indicate higher delay contributions. And I don't want to go into all parts, but I just want to make clear that not only the transmission path over the network is relevant for the delay. So, for example, we have the driver buffer of the sound card, or also the transmission in the air between the sound source generation and the microphone, or the loudspeaker and the ear, has an impact on the latency. So it is important to understand that also the equipment you use and the environment in which you're doing a network music performance have an impact on the latency. Now, I will talk in more detail about the topic of synchronization, about the impact of latency on synchronization and how to cope with it. So, to play in sync with a stable tempo, network latency is the central issue. Practical tests in which the physical distance had been increased stepwise between two musicians showed that beyond approximately 8 to 9 meters of separation, a rhythmical music interaction without a conductor in the middle becomes too difficult in terms of keeping a common tempo. This corresponds to a threshold of about 20 to 30 milliseconds, which can also be called the ensemble delay acceptance limit. And of course, this threshold depends on different aspects. For example, the musician abilities, the playing tempo, type of music, instrument characteristics like timbre and attack, and the used delay compensation strategy. So let's take a look on an example here. So if we assume that we have two drummers playing together on a bidirectional connection, so we want an interaction between both of the drummers. And drummer 1 plays a rhythm, and we have a one-way delay of 20 milliseconds. Then player 2, the drummer 2, can only react after 20 milliseconds of audio transmission. This means that drummer 1 hears the reaction of his colleague just after 40 milliseconds of delay. So to illustrate this, we now hear a rhythm from the position 1 of drummer 1, which I have delayed by different delay times, with a one-way delay of 0, 8 milliseconds, 20 milliseconds, and 35 milliseconds. So I will start now the playback. So I think the challenge at high latencies is obvious. The rhythm at the end had nearly nothing to do with the beginning rhythm or the starting rhythm. So, but the musical interaction between two musicians behaves a little bit different. So several hand clapping or rhythmical experiments, which were evaluated with some objective metric like asymmetry, imprecision, tempo slope, regularity, pacing, or mean lag, these experiments showed a tempo acceleration in the range between 0 to 8 milliseconds caused by the subject's tendency to anticipate. In the range between 8 to 25 milliseconds, best synchronicity was achieved with a stable tempo. And in a range between 25 to 60 milliseconds, a tendency of deceleration occurs and delay compensating strategies were needed for the musicians. And at higher delay times, higher than 55 to 66 milliseconds, the playing accuracy rapidly falls off and it becomes really difficult to interact with each other. So here now we have some videos. Check here. We have 2 videos of an experiment we conducted in our institute. We have 2 subjects playing some kind of complementary rhythm, and we have a leader and a follower. So the leader starts and the follower follows after 2 bars, and they're playing this rhythm first with a delay of 15 milliseconds. This sounds quite good. And if we now hear the same subjects in the same condition, but with a delay of 66 milliseconds, I will start. And I hope that you were able to hear it, that after the point where the follower starts playing, the common tempo of both players rapidly falls off, though we had quite a good example of tempo deceleration caused by the high delay. So there are multiple strategies which were proposed by Caro and Werner in 2007 to cope with latencies. So the most effective, but technically the most challenging strategy is simply to keep the latencies as low as possible. This is called the realistic interaction approach, and this allows the most realistic interaction, especially in terms of immersion and co-presence. If this is not possible, there are other strategies like the master-slave approach, which where the musicians have fixed roles, like in the video you saw before, the leader and follower roles. There exists some kind of the laid-back approach or the delayed feedback approach, where the local sound is additionally delayed to the transmission path or to the transmission delay of the network. A more artistic approach is to use the delay as some kind of musical language, the latency acceptance approach, and there exists the approach of normalizing the latencies. So in the LIPS project, we focused on the realistic interaction approach with the highest technical challenges to allow the most realistic interaction in terms of immersion and co-presence. And this brings me to my conclusion of the conclusion of my presentation. So to provide a high-quality interactive experience, realistic performance conditions must be guaranteed. So what are these realistic performance conditions? So we need some kind of acoustic environment. This means we need high-quality audio transmission, we need some kind of low-latency audio processing, and we need a virtual auralization, room auralization. Second, we need some kind of immersive video or virtual environment. So we need a virtual visual environment, a mocap system, tracking system, or we need a high-quality video recording and playback and light adjustment. And to reduce latencies or use delay compensating strategies for higher delays, a high-quality network connection is needed, some kind of synchronization at the locations, network monitoring, and perhaps a global conductor. And of course, at the end, we need musicians which want to play with our system. And I know that we will work on all these aspects in the next 3 hours. And so I just have to say, if you're interested in more details about network music performances, here you have an overview of my used references. And I would especially like to mention the lecture Network-Based Collaboration Music Making by Stefano Fasciani, from which I also took some ideas and content for my presentation. And if you want a good basic introduction on network music performances, I can only recommend this video. So thank you very much for your attention, and I'm happy to answer your questions.
Thank you, Robert. So I see there are no technical questions. So maybe I ask a question. Robert, you had 3 parameters for network performance in your talk, and based on your talk, the latency was very, very critical. Can you explain how the latency depend on the other parameters like bandwidth?
Yeah, I think this is not a question I can't easily answer in one sentence, but I have to say, or I can say that, of course, theoretically, there is a dependency between latency and bandwidth. So theoretically, if you have a really high bandwidth, you should have a low latency. But you can't say that this works all the time or in general. So there is this nice picture of a truck with thousands of hard disks traveling from Munich to maybe Hanover or to Wedemark here. So you have thousands of gigabit on hard drives, so you have a high bandwidth, but the truck needs 7 hours to travel, so you have a high latency. So it can happen that you have a high bandwidth, but not a low latency. So to be honest, I am not a networks professional, so I can't really answer this question on the technical way, but I know that it's not always in general that with a high bandwidth you have a low latency.
Thank you. I see we have something on YouTube. There's a question coming in over YouTube. Are the 8 to 25 milliseconds optimum one-way latency or round trip?
No, it's one-way latency.
It's one-way latency. Okay, thank you for clarifying, Robert, and thank you for your talk.
Yeah, you're welcome.
So we are very good in time. Today, we have planned 2 technical sessions and a live concert. The technical sessions A and B will be before lunch. The concert will be after the lunch break. It is so to your advantage to stay tuned in. There was also a question coming in if we can make the slides and the presentation available after the workshop. I will certainly check, but I don't think there's any reason not to do it. It will be on our website where you already registered for this workshop. We will now start with our first technical session. Again, if you have any questions, you can put them in the chat box in YouTube or send them directly via email. If we have too much questions coming in, I have to select them due to time limitations. Nonetheless, you can contact us directly after the workshop via the email on our website. So our next speaker is Dr. Jan Dürre. Jan, are you there? Hello.
Hi, Jens. Nice to see you.
Nice to see you too. Good morning. So you are giving a talk about ultra-low latency audio network transmissions for network music performance?
Yes, you're right.
Okay, then the stage is yours.
Okay, thank you. So my name is Jan Dürre. I'm with a company called Sennheiser. And within LIPS, we were responsible for implementing ultra-low latency audio network transmission for network music performance, as Jens already said. At the start of my talk, I want to again explain the challenge we had within LIPS. So what you can see here now is a typical, of course, simplified stage setup where 2 musicians are rehearsing or playing for an audience. What you can see here now is one musician with a guitar and a microphone. So these are two audio sources and a headphone. This is an audio sync for him. And a second musician that is playing the drums. This is an audio source, and he has also a headphone as a sync for audio. Both musicians are connected via mixing console, and this mixing console creates two feedback loops for both musicians that are necessary for them to be able to play and to be creative together. One feedback loop is the self-feedback. So this is necessary for the musicians to hear themselves. This feedback loop has a very strict requirement regarding the latency of 4 milliseconds, of about 4 milliseconds. And secondly, there's an interplay feedback loop. This is necessary for the musicians to hear each other. The requirement for this latency, as Robert in the talk before explained a bit, is a bit less strict, but still challenging with 8 to 25 milliseconds. If we now think about a network music performance, so both musicians are distributed on two different locations, the simple approach is this. So we duplicate the mixing console. This allows us to keep the self-feedback delay still easy below 4 milliseconds. And the challenge for this setup and the wide area network connecting those mixing consoles is to keep the delay below the interplay feedback requirement of 8 to 25 milliseconds. Our approach within LIPS now, since most mixing consoles are not that easy to plug onto a wide area network, was now to implement an interface device that is able to connect generic audio devices, for example, mixing consoles, to wide area networks, and thus creating a low latency audio tunnel between both locations. This is the device we implemented within LIPS. It is powered by an FPGA and ARM SoC, and it has two main interfacing connectors. On the one hand, here marked in blue, this is high quality analog audio in and out. And on the other side, in orange, marked here in orange, there's Ethernet connectivity that allows us to transfer or translate audio from the analog to the IP domain. This device we called audio network transmission, or short ANT. With this dedicated hardware, we are able to give a very detailed and also constant audio latency budget. This is what I would like to present with this slide. Here you can see on the top the location A, and on the bottom location B. Both have a mixing console and the ANT devices connecting both locations over a network. So if you now look at the latency, starting at location A from a microphone, the signal runs through a mixing console. The mixing consoles we used within LIPS introduced a delay of 850 microseconds. The signal then travels into our ANT device, where it is translated from analog to digital. This takes about 125 microseconds, and this is driven by a local sample clock A. After that, the samples are packaged for network transport. The number of samples we take for each network packet is arbitrary and forces us to do a trade-off between delay and network overhead. Packets are then sent over the network to location B, where they are fed into a jitter buffer to achieve a constant delay. And then we have an important block, packet loss concealment. The latency for this is very low, but it is very important since we are using unsafe transport protocols. Packets can be lost, and we have to conceal these for the artist. And for the final step, the transversion from digital to analog, we have to to resample every sample because at location B we have a different sample clock that is not necessarily related to the sample clock at location A. This resampling also forces us to do a trade-off between resampling quality and delay. If there is a synchronization service available, we are able to synchronize sample clocks, and this allows us to remove the resampling. And furthermore, within LIPS, we decided to use 500 microsecond large network packets for the network transfer. This sums up to about 1.7 milliseconds of latency just through the mixing consoles, and the processing in our dedicated hardware devices is about 0.8 milliseconds. The unknown part yet is the network transfer and the jitter that is introduced by it. Before I show you some measurement results we achieved within LIPS, I want to give you a bit more context. The distance between Munich and Hanover is about 500 kilometers. And if we think about a fictional direct copper wire between Munich and Hanover, the propagation delay between those locations is theoretically at least 2.5 milliseconds. So we can see this as a lower latency limit for the connection we introduce here. For the real implementation of this interstage connection, there are several commercial products available that differ in performance classes, for example, bandwidth or other QoS parameters. The LIPS consortium decided to select a product that is a layer 2 fiber connection with 1000 megabit per second and a guaranteed QoS parameter by the network operator with a latency of below 18 milliseconds and a latency jitter below 3 milliseconds. And on a side note, this realization of the network connection cost an initial fee of 7,000 euros and a monthly fee of 1,800 euros. Since we have a synchronization service available, we are also able to do very precise latency measurements of the network. And this is what I want to present with my last slide. Here you can see real measurement results. Within LIPS, we transferred 6 audio channels in each direction from Hanover to Munich and from Munich to Hanover. This sums up to about 10 megabit per second in each direction. And on the bottom left, you can see a logarithmic histogram of the latency of every packet, every audio packet that we have sent within a rehearsal session of about 2 hours. What you can see here now is that most of the packets have a latency of about 5 milliseconds. And the jitter goes up to about 5.6 milliseconds. Based on these measurements, we designed our jitter buffer with a bit of headroom for safety with 1 millisecond, resulting in an overall network latency of 6 milliseconds. So to sum up, within LIPS, we achieved a mouth-to-ear latency from Munich to Hanover, including a mixing delay of 1.7 milliseconds and a processing delay in our ANT devices of 0.8 milliseconds, of outstanding 8.5 milliseconds. Thank you very much. And of course, I'm available for questions. Back to you, Jens.
Thank you, Jan. Very impressive talk. Yeah, so we have no questions coming in for your talk, so maybe I ask a question.
Go ahead.
Based on your talk, latency seems again the most critical value here. And although the result is very, very good, in my opinion, the network latency is 5 milliseconds. Could you explain how that is achieved? Can it be reduced, or what are your thoughts on that?
So one important factor here is that the actual topology of the network is unknown to us. So before I made an estimation that is based on the theoretical premise that we have a direct wire laying from Munich to Hanover. The delay with that already summed up to 2.5 milliseconds. Now in reality, this looks very different. There will be multiple, for us, unknown network nodes between Munich and Hanover, and also the length of the connection will be much higher than these 500 kilometers that would be a direct line of sight. So there are a lot of unknowns within this network, and all these unknowns sum up to the latency that we are able to measure.
Okay, thank you. So we have questions via YouTube coming in. Maybe I start with the first question is, will the UNT device become commercially available?
So I have to emphasize here, this is a research project, and I'm also part of a research team. And this is not even a pre-development yet. So I can't say really something about that.
Okay, thank you. Another question is from YouTube is regarding the audio encoding. Did it introduce much more delay?
So within LIPS, we used uncompressed audio. So we did not encode the audio for the transmission, but nonetheless, this is an option in our ANT devices to actually compress the audio. And if you use the right codecs, and we have some of the right codecs, the delay that is introduced by the encoding is very, very, very small, below 20 microseconds.
Okay, thank you, Jan, for clarifying that. We have another question via YouTube. Again, it's about latency and jitter. Did you do some test with a standard internet connection, and how much latency and jitter would that have?
So we within LIPS we did not test this. But on a side note, I can give an anecdote about that. We tried out this device from our home. So a colleague of mine took one device to his home, and I took one to my home, and we connected them. And I think we achieved something of about 20 milliseconds there.
Okay, it's more than double. Thank you, Jan. And we are now switching again to Munich, to our next speaker, Hermann Popp from ARI. And Hermann, where are you? There, I see you. Good morning. Good morning, Hermann. Can you hear us?
Yes, we can hear you.
Perfect. Okay.
Right slide here.
Yeah. Yes, we can see it now. Okay.
The talk is about light and image, very important also. ARI has addressed this. We will go through it. Yes, the vision of LIPS clearly was linked to locations in a most immersive way. Imagine a wall disappears here and the remote room gets visible to you, close to you next. We want to do this in a very natural way. We want not to have any studio feeling. We want to have natural light. And this was one of the requirements we tried to address. So it was clear we do not have to deal only with the image path. We also do have to deal with the lighting path. When you take care also of the lighting path, you have the option also to design the image path a little bit different than this is done before. This is also addressed in LIPS. This is roughly the structure of the ARI subsystem for LIPS. At the top, you see the lighting, below the imaging part. The red boxes, let's start with lighting at top. The red boxes at each scene represent spectrometers that are taking the light very precisely in the scene. Since both locations are mostly symmetrical, just connected via this 1 gigabit Ethernet link in a bidirectional. Yes, the spectrometers measure exactly the lighting in the scene at both sides. You, of course, have lighting devices you see here, mainly flat light for adaptation with natural light, also some spotlight. But the third part, very important, ambient light. This is natural light that we want to use as much as possible. There's a lighting gateway that is gathering this information and makes it available via IP, since not all devices are IP enabled in the moment. This does the gateway. Very important is the blue box below here. That is the so-called lighting control. That is collecting the spectral information from both sides, calculating a common value for both sides, and driving the light specifically at each location to match a common target value. With respect to the imaging path, you see here the blue box is the cameras at both locations. They have two functions. They have a normal camera function, so sending via IP, but in parallel, they are receiving also the remote stream and sending it to a large display. Both functions are in this camera integrated. The whole system is synchronized. The red box is below. This is subject of a talk later on. This allows to have all systems, lighting and camera in sync. A lot of work had to be done. The work package at ARRI have been divided, of course, into lighting and imaging. But we also in the vertical axis separated into basic device technologies as is needed and also services on top of that. We will go through this a little bit in detail. Let's start with lighting services. Yeah, the goal was clearly to have matched lighting, but it shall keep natural light as much as possible. Some people call it minimal invasive. Do it very careful. Very important, already mentioned the two spectrometers, two at each side that measure light precisely. You see here a screenshot of the spectral distribution. But these are also able to deliver derived parameters. And when dealing with natural light, the so-called CCT coordinate system is very good, very suited. Stands for correlated color temperature in Kelvin, given in Kelvin, equivalent to a radiation of a black body at this temperature. So parameter number one, parameter number two, in case you are a little bit away from this ideal curve, due to windows very often, you also get this deviation. And of course, you need the absolute light intensity as people see it. This is given in lux. This is a screenshot of the lighting control that has been developed for LIPS. The structure is quite simple. One column here for Munich, the other Hannover Wedemark. On top, you see the 4 spectrometer values. In the middle is the common target value to that both locations are adapted. You see here the lighting control that is necessary to reach this target. This is a continuous process with a cycle time of some seconds. It's permanently running. One thing has to be mentioned. The spectrometers, when the system is in operation, is permanently collecting the superposition of artificial and natural light. The target value should be based just on natural light, so it has to be separated. This is possible based on a calibration process we do at the beginning of the performance, and then you can run it continuously. Just a few to the lighting devices, the lower level we need. You see here a picture of the spectrometers are quite compact, nevertheless quite precise. Several devices have been evaluated in LIPS. They are absolutely calibrated. They are IP enabled. You can operate them remote over the network. And they're also handy. They are able to be operated single cable with a single cable, and power over Ethernet option was developed for these type of spectrometers as a manufacturer, free of charge, just for LIPS. It's quite a good, precise device. The device is in the scene and has a 360-degree sphere to collect the lighting, the complete representative lighting in the scene. This is a picture of the lighting gateway. We talked about it. IP control for our devices, IP synchronization is possible, and also it provides the power for the spectrometers. With respect to the lighting devices themselves, for a good superposition of natural and artificial light, it's important to have a solid baseline. You see in the top window that are placed close to the window for a good superposition. A large diffuser that avoids blending and other effects. And for scene enhancement, we have also spotlights. These are the two types of devices that are used here, all under control via IP. Now we come to imaging, the right column. The goal is clearly to have an immersive image path, an authentic reproduction of the scene. We want to have everything original, size, brightness, color. So these were the clear requirements for the design of this image path. It is clear you need a linear path. You have to be sure it's really linear, so the calibration is needed. And it shall be free of any automatic mechanisms that may compromise the result. And this has to be said is just possible if you have matched lighting. The reason is the observers at both sides are matched to the same white point matched with respect to colorimetry. And this allows to operate the system with the floating white point of natural light. This is normally not the case, but possible in this situation with matched lighting. Imaging services also has to take care of the design of the whole image path and to provide the right numbers to the camera and the whole system. Several decisions are needed. It starts with the color space. We are using the widest currently defined color space. It's not fully matched by displays currently, but the probability that you fall out is quite low. You need an absolute control of the luminance of the displays. This is possible. There's a standard for this. Was introduced in high dynamic range imaging came. It has two very important features. It defines absolute deceleration of digital numbers at the input of the display and the luminance at the output. And secondly, in a very large contrast range and in parallel, quite efficient. The quantization is based on human perceptions. That's the reason this curve is called PQ in the short form. Of course, the system can make use of the very comprehensive digital linearization of these cameras that are in use, and also other processing tools, for example, 3D lookup tables that allow to map every color space on the input side precisely in the desired color space at the output side. This gives you a visualization of such a cube. Last point, very important, is a calibration of the display. Image services also took care of this. You see here at the picture. It was very carefully analyzed and finally checked between the scene and the representation of the image. By spectrometers, you can check that it's exactly matching. You need, of course, devices for imaging, mainly display and camera. For the displays, the requirement was to clearly match the standards that we have talked about. Also important, it has to be free of artifacts. This is not absolutely clear for every device after looking into it. And it must be calibratable. And also this point was critical. Calibratable means it has to have a constant behavior over time. And if you look carefully at the devices, they may come up to a point and then falling down. You cannot use this. This is no defined characteristics. So this was a big selection process. We tested several devices. You see here, it's very heavy, big machines that were carried in and carried out. Finally, we are using OLED displays that are fulfilling the needs so far good. They are limited in luminance, but in the scene inside of buildings, it's sufficient. A word to the camera. The challenge starts at the image sensor. At least for single chip cameras, it is tried to match the color filters closely to that of humans. You see here RGB, that is the characteristics of humans. It's not a standard curve. But if you do so, you have the benefits that you have the full gamut of humans and also the discrimination capabilities of humans. Of course, the image sensor has also to provide high contrast capabilities. In the scope of smart service world, we had limited bandwidths. 1 gigabit was mentioned. Roughly half of that is used for the image path. For a high quality image, this means you have to compress it. This is also done. It has to be done low latency. We are using a so-called intra-frame compression codecs that can do this. And finally, also not to forget, it's a big difference to audio. You cannot, when you get the image from the compressor, you cannot put it immediately on the line. First, it has not the capacity. Second, you are not allowed to block the line because there are other services, all IP, for example, synchronization, also audio and so on. So we have to distribute it. This is very important for these kind of services. And finally, the camera itself, as mentioned, is also synchronized. The camera, as mentioned, second function is receiving, clear decompression and also error checking and fault tolerant output to the display. A last statement I want to make, we are talking here about streaming, but it's absolutely clear that when it comes to high quality material, that you want to reuse it. And this means you will go to the file domain. And this should also be considered. There is a standard that allows it called MXF Media Exchange Format. You see the numbers here. That is worldwide in use in the file domain, but its design and principle are also suited for streaming. And this has big advantages because it allows you to have data consistency in both worlds. You can go from one domain to the other without any conversion process. No risk of losing any metadata, for example, that are important at more complicated productions. So this shouldn't be forgotten. MXF Live is the label for this. And at least according to our knowledge, the LIPS cameras are the first that are supporting this, at least in this camera class. Yeah, we want to say thank you for the Ministry of Economics for funding this project, also the DLR for managing. Many thanks to the universities for music and theater in Munich and Hanover, and the students that did very impressive music performances you can enjoy later on. We thank you for your coming. And of course, all the LIPS colleagues that made this project alive at ARI, I would thank very much, especially these colleagues. Thank you very much.
Thank you very much. Okay, so we are moving on right to our next speaker. It's Marcel Nopput from the Leibniz University of Hanover.
Hello. Yeah, hello again.
Okay, so you're giving us a talk towards immersive network music performances, right? Yeah, perfect.
That's right, yes.
So the stage is yours.
Thank you, Jens. So hello and welcome to my talk towards immersive networked music performances. My name is Marcel Nopput. I'm a research assistant at the Institute of Communication Technology at the Leibniz University in Hanover. And today I would like to present you the topics me and my colleagues have worked on in the course of the LIPS project. First, I want to show you how we imagine immersive networked music performances. After that, we will see a short video of a demonstration setup at our institute. And finally, since we focused on audio, I will present the key technologies that are necessary to create audio immersion for networked music performances and our related research topics. Let's start with our vision for networked music performances. We have two musicians here, a guitarist and a singer, who are in different rooms at different locations, and they want to make music with each other. What if they had a virtual window in their room, which allows a room into their friend's room, a view into their friend's room? On the visual level, that means they have a perspectively correct view into the other room, no matter where they are standing. On the acoustical level, that means that they perceive a room acoustic that corresponds to a larger room, consisting of the two individual rooms. This would create an immersive, interactive coupling of geographically separated rooms, just like a virtual window. In the following video, we would like to present an experimental setup at our institute where we created a unidirectional virtual window. For the full spatial audio experience, please use headphones. Enjoy.
Hello and welcome to our Immersive Media Lab here at Leibniz University in Hanover. This is our laboratory where we can interactively reproduce three-dimensional audio scenes in combination with a video projection system. Today, we want to show you a demonstration of our virtual window, an audio-visual representation of two coupled rooms used as an environment for immersive networked music performances. Our front screen is driven by signals coming from a game engine, and it provides a view into the room beyond the window. The acoustic scene is dynamically rendered using higher-order ambisonics processing, and it provides plausible room acoustics of the coupled rooms. By tracking the position and orientation of the person in the room, a perspectively correct video picture is shown at any time. Position and orientation data is also used for the spatial audio rendering. Room acoustic properties and source directivity are also considered. Therefore, even moving sound sources are reproduced correctly. Thus, the impression of a virtual window becomes more realistic. This is how this acoustic scene sounds like in binaural audio. Later, this technology can be used in a virtual collaboration space where all movements of a person or a musician are captured and represented in the connected room.
As we have seen in the video, we need a considerable hardware setup and some advanced signal processing techniques to implement the system. As I've mentioned before, we focused on the audio immersion. Let us now take a closer look at the signal processing subsystems that are necessary to create audio immersion for networked music performances. These subsystems are depicted as yellow boxes here. The first building block is the virtual acoustic rendering that is controlled by a source and listener tracking. This is performed by the rendering framework that you've just seen in the video. The general signal flow is illustrated in the figure on the right. So we have a customizable virtual environment in Unreal Engine. We have a versatile video playback through a projection screen or VR goggles. We have the audio rendering framework with controllable room acoustic parameters and various options for user control. Our work results are the framework itself and a study on room acoustic measurements in virtual acoustic rooms. In the future, we want to extend this framework to virtual room acoustic for the own voice or the own instrument and a bidirectional setup. So we have a virtual acoustic rendering and a source and listener tracking. But how can we obtain the room acoustic parameters that we need to do a plausible virtual acoustic rendering? We want to use estimation techniques for that. By comparing the sound field of the directly incident sound and the sound field that is created by the wall reflections, we can estimate the acoustic reflection coefficients of the walls. We used spherical array microphone processing for that. So far, our method can identify first-order reflections for simulated and measured data, and reflection coefficients in a certain frequency range can be estimated with a relative error of 3.5% for simulated data. The obtained room acoustic parameters can then be transferred to the virtual room model, which enhances the acoustic rendering. So we can do a plausible room acoustic rendering now. But of course, the bidirectional acoustic connection of the two rooms causes echo and feedback loops. That is why we need acoustic echo and feedback control here too. We worked on both topics, acoustic echo and feedback control, but we mainly focused on acoustic echo cancellation. To address acoustic echo and feedback problems, a common approach is to add an adaptive filter, which works as an acoustic echo or feedback canceller. But acoustic echo cancellation systems are usually designed for speech communication, and immersive networked music performances imply some new specific constraints, such as we are dealing with high-quality musical audio signals, which means higher sampling rates, longer filter responses, and the general requirement is good sound and not speech intelligibility. We have a delay-sensitive application, which means an increased demand on low-delay processing, and the interplay of musicians means a continuous double talk, which makes it harder for the adaptive filter to converge. The multi-channel playback introduces the non-uniqueness problem, which means the underlying mathematical problem is underdetermined. We have created a versatile simulation framework for acoustic echo cancellation methods, and we have conducted several studies on echo cancellation for immersive networked music performances. This is our proposed setup system for audio immersion for networked music performances. Some building blocks I just presented are already implemented in our system. Some shall be integrated in the future. Beside the presented topics, we've also worked on a global metronome. These devices create highly synchronous click signals and visual cues, even when they're located thousands of kilometers apart. In our studies, the metronome helped musicians to cope with audio delay in networked music performances. As mentioned earlier, we have also looked into feedback control. We've experimented with traditional approaches, but also with adaptive feedback control techniques for our application. I hope you enjoyed my talk about audio immersion for networked music performances. Thank you for your attention. I'm now happy to answer your questions.
Thank you, Marcel. So I see we have no questions coming in at the moment. Then maybe I will ask this question because as you can see, I don't have headphones and I really would like to listen what it's like to have this virtual room. How can that be achieved?
Well, you could come to our institute, visit us, and we could give you a demonstration. If you're interested, contact us via email, and maybe we can arrange a visit. So this is a demonstration we could run out our institute.
Okay.
And for a first impression, just review the video and use headphones. That's it's worth it.
Thank you. We have some questions coming in via email. When will such a system be available? This would be perfect in Corona times. So what are your comments on that?
Yes, well, the Corona times and the pandemic situation is, of course, a huge motivation for us to work on these topics. Even although the project started before the pandemic situation, we are a research institution, so we're not working on product developments. So it will not be commercially available, but we hope that our works can improve future products, and so these may be available someday.
Thank you, Marcel. We have another question via YouTube, and it is how many audio channels are translated between the rooms?
Well, we are now working with ambisonics encoding and decoding, and so far we work with third order ambisonics. So this is 16 audio channels. future studies may show if this is sufficient, or if we can save channels, save data, or if we need more channels. This is still a subject of research.
Okay, so thank you. We have another question via email. It's can you somehow measure the amount of immersion? Is there a metric for it?
Interesting question. No, not yet. But this is would be an interesting study to compare different settings of the system and to evaluate the degree of immersion. This would be interesting, yes. But we haven't worked on this yet.
Okay, thank you. Another question is here. A statement is Skype. You know Skype, obviously, Marcel. Skype works good as now. Why is audio-video immersion necessary?
Well, for speech communication and for speech intelligibility, maybe this state-of-the-art systems are sufficient. But studies show that the stress that you perceive in speech communication with some commercially available systems, that the stress level is higher than the stress level you perceive when you sit opposite to each other in a room. So immersion may even improve these systems. But our application is a musical application, and then the immersion is much more necessary because musicians need the contact in a room and the room acoustic that they perceive when they are together in the rehearsal room.
Okay, thank you, Marcel. So I would go for a short break now until we continue with our technical session B. We will back on 10:45, and everyone can take a coffee from the viewers or any other needs. So we will be back shortly. Okay, welcome back. Hello. We'll start now with session B, but first I want to announce a quick note and reminder. Some questions are coming in via email, which are a little late, and regarding past talks, we will relay these questions to the appropriate speaker and answer directly via email. So we are now switching to our next speaker in Munich. It's Georg Acher from Mobile Labs. Hello, Georg.
Hello. Thank you for your nice introduction. I'm Georg Acher from Smart Mobile Labs, and we are working in the environment, well, let's say, for the link, for the IP, for contribution and distribution of images. And since we have a lot of videos in our talk, we have a pre-recorded presentation. And, well, let's start it. Our presentation is titled Tools and Services for Live Remote Production and covers the main aspects of our LIPS sub-project called MICAPS, Mobile Edge Computing for Interactive PMSE Services. I prepared this talk with my colleague Detlef Flegel. Now, as Smart Mobile Labs is probably not as famous as ARRI or Sennheiser, I'll shortly talk about us. Generally, we do low latency streaming with focus on mobile networks. Here you see a live video stream from a race car on the Nürburgring over a 4G network. We work on video contribution and distribution with specialized hardware encoders and decoders, as well as streaming software, customized services, software clients, and apps. Here's an example in the area of public safety. You see a firefighter equipped with a 4G streaming encoder and a camera, and a supervisor can view the scene from the firefighter's perspective, supporting the mission. We install 4G and now also 5G campus networks, like the station for the famous 24-hour Le Mans racetrack. And we also work on mobile edge and cloud computing infrastructure for our services, like in this multi-screen streaming with 4G over our edge video orchestrator for a basketball game. Now to our work at the LIPS project. We provided a LTE base station and multicast services over our edge video orchestrator. This was done in cooperation with Sennheiser Streaming Technologies, and Alexander Beifus from SST will talk about this later. Based on the main LIPS scenario, we analyzed what it needs to provide low latency audio-video streaming, what cloud or mobile edge cloud services are required, and which audio-video handling or workflow concepts seem useful. For the LIPS event itself, we provided network and video. I will go into details later. We also developed some useful IP-based gadgets for production support, as well as software tools and services. Then we worked on further integration of IP-based and conventional audio-video workflows. Finally, a lot of work went into the field tests. These were the LIPS concert and also a very challenging outdoor event for aspects not testable in the concert setup. Now we have a look at the works for a concert environment in Munich and Hanover. We prepared the network access for the project partners, and that included planning, installing network devices, and also network setup tasks like quality of service or VPN for external remote access. Besides the main audio-video handling by ARRI and Sennheiser, we did video recording and streaming of 2 cameras on each of the event locations. We heavily tested our new dual video encoder platform. This allowed documentation of the rehearsals as well as an easy live observation for the project partners not present in Hanover or Munich. We worked on gadgets, tools and services to expand our existing capabilities for IP-based remote production. It should be noted that we want cost-efficient IP usage, as it only makes sense to replace traditional interfaces like SDI when it reduces costs and efforts. So we target the usage in typical network environments without premium or carrier-grade network infrastructure. Here you see a wireless LAN control interface we have developed for an inexpensive camera gimbal. This is a portable wireless LAN telelight for a camera operator. In combination with a Blackmagic video mixer, you can indicate on-air, preview or other states. We also did software developments for custom off-the-shelf video encoders. Such standard but modifiable hardware products are very important for most of our use cases. Now some words on cloud services. You see the brackets around mobile edge. This is a result of a market development since our project proposal. MEC moves computing resources to the edge of a mobile network, which mainly reduces the network communication latency for the user equipment. But there are still no standard implementations or real business concepts, so I have looked at useful services for generic clouds, including the MEC. That involved topics like service discovery, network and audio video stream monitoring tools, and processing of video, especially with GPU support. One development for such a cloud service is a GPU-accelerated H.264, H.265 video encoding and decoding based on NVIDIA GPUs. We have reached a very low end-to-end latency streaming, which is highly customizable and runtime adaptive, like for link speed, burst bandwidth, and so on. A special feature of our system that makes it ideal for one-to-one connections is that iframes can be sent only on demand, like at startup or stream errors. That reduces the bandwidth. We also developed more tools to support cost-effective hybrid productions, combining IP-based devices with conventional devices. This is our hybrid intercom system based on voice over IP. The client devices are simply smartphones with headsets. The underlying system can also connect to analog I/O or a DECT-based intercom. We implemented a hybrid and flexible network concept that allows connecting and adding new devices like video encoders on the fly to wireless LAN, fiber and Ethernet connections anywhere and in any chain position in the network. Here's our lab test setup. You will see a real-world usage of this concept in a minute. Also, we put a lot of work in a reliable IP-based contribution with an SDI breakout to a conventional video mixer. These dense rows of tiny connectors at the backside of a PC are the SDI outputs of two Blackmagic Decklink quad cards. They output the video of 8 H.265 streams decoded by a GPU. All these developments were then combined in our second field test, the Jena Stier 2020. This was the very first full live coverage of a ski mountaineering contest. It took place in February 2020 at the Jena near the Königssee. As you can see, the racetrack area is spread over 700 meters in height and covers slopes as well as unprepared forest ways. And now we know why we were the first. Such an event coverage is simply not possible with conventional production methods. We had 7 fixed and mobile cameras in the field as well as a drone. Here are some impressions of this production. The whole production was managed and run only by Detlef and me. Due to bad weather, we only had 2 days to set up our full equipment. The actual racetracks and as a consequence the final camera positions were known only 1 day before the race. We were able to use the fiber network of a Jena barn at the middle and top station and installed wireless LAN link antennas pointing to the camera locations. At these locations, 1 or 2 camera operators shared this common radio link. They carried the equipment by ski and set it up just in time at the day of the race. The first camera signals reached us 30 minutes before the race actually started. The central component was a mobile encoder box containing video encoder, wireless LAN access point, a battery, LAN PoE and a fiber interface. The box has an SDI input for the camera and spans a local wireless network for tele and intercom. Here you see such a box connected to the link antenna. There's also another encoder box 300 meters away connected over a fiber wrapped around mountain pines. So this encoder also acts as a relay station. All network streams arrive at the top station, are converted to SDI and mixed with local cameras. And this is one of our operators with his camera and a tele gadget on the top of it, the encoder box in the front and our intercom headset. In the back you see the top station where we were located. And with these pictures we will close our presentation with some conclusions about the LIPS project. We gained precious knowledge about the hard requirements for such indoor and outdoor events. We got a lot of hands-on experience. We developed various concepts, useful gadgets, tools and services for support of this type of production. We survived even a serious, challenging and ice-cold field test in its literal sense. And overall we demonstrated that even under difficult conditions, cost-efficient IP-based productions are possible. Thank you for your attention.
So that's it. I hope you were entertained. It's not everything that has to be done with music here, but I think all the important parts with IP linking, cameras, audio, and the combination of everything together is an important part in our work. And Ari and Sennheiser cared perfectly about the concert setup. So that's it.
Okay, thank you, Georg. I will have a look if we have some questions coming in. In the meantime, I can ask you a question. It was a quite interesting video you showed. As far as I understood, you did an all IP production. Do you think this is the way forward for PMSE?
Yes, I think it is, but you have to think about the costs. That's the main point. It doesn't make sense to replace the conventional standards like SDI or whatever just by IP if it's getting more expensive than the current standards. So the idea is that you should use the traditional conventional hardware for networks, not carrier grades, not premium, whatever, and think about what you can save, and not that you have to add extremely high cost network hardware like some current developments are, let's say, underway.
Okay, thanks for the insight, Georg.
Okay.
And we will now continue our technical session B with our next speaker coming from the University of Erlangen-Nürnberg. It's Heiko Bruckmeier. Heiko, so you are not in Munich.
No, I'm here in Erlangen. Thank you for the introduction, and hello to all our listeners over the internet. I am Heiko Bruckmeier. I'm a research assistant at the University in Erlangen-Nürnberg, and for the next few minutes I will talk about synchronization and the challenges for distributed live performances. The first question I want to answer is why we need time synchronization. I try to explain it with a simple use case. In that use case, we have two sites A and B, each side equipped with a microphone, camera, and, for example, a metronome. These two sites are connected via a wide area network. Yeah. At each side, video and audio stream is produced and sent through the network to a remote production room. As a remote production room, we want to produce a joint production so that one can listen to both side A and side B produce streams at once. So for example, if the audio and video stream that are received at the remote production room are not synchronous, it can happen that at a joint production, the video and the audio you hear and listen to, see and listen to, are not in sync. Another example is, as mentioned before, also the metronome or a virtual conductor. So for example, if two musicians want to play together or want to practice together at different rooms and play to a metronome, for example, and click, these two metronomes must be in sync or in time, so the musicians can play together in synchronized and in time. These all needs synchronization, and all these devices have to be in the same clock domain to achieve this result. If we want now to perform a synchronization over the wide area network, this introduces some challenges. The first challenge is the distance between side A and side B. This distance, of course, results in a transmission latency, but that's not the only thing. Usually, the network between side A and side B is an unknown network, so we have there some more unknown parameters. For example, we don't know the path the traffic takes through the network. The routing of the traffic is unknown, and another point are the number of hops or switches that are in between. Additionally, there may be a cross traffic that interferes our traffic itself. All these unknown parameter results in errors like latency jitter, asymmetry between site A and site B, and the last thing, packet loss. To overcome these errors, for better understanding, we can divide these errors in 3 types of errors. The first error is the static error. Static error is just a constant error over the whole time, so like the asymmetry or the average latency. The second is the dynamic error, which changes quickly over time, like the latency jitter and the packet loss. And the third type is the pseudostatic, that are usually static errors that changes from time to time. For example, if the routing between site A and B is changed, then the average latency is also influenced and changed in that way. It is also an example why it's difficult to overcome these pseudostatic error, because if the routing is changed between the sites, you can only measure that by the round trip time. If the round trip time is changing, then it could be that the average latency changed or maybe the asymmetry is changed too. This can be determined in detail with just measuring the round trip time. In contrast, therefore, the static error can be solved by measurement or calculation before you start to synchronize your system, and the dynamic error can be overcome by filtering out the jitter. There are some methods already existent, which with that method you can synchronize your sites together. The first is the dedicated cable. You can connect all your devices or the sites with a dedicated cable where you can perform a synchronization through it. For example, a frequency signal, frequency synchronization, or synchronization with a pulse per second signal. This is not that easy to use for a wide area network, because if you have 2 sites that are a few kilometers away from each other, you cannot connect these 2 sites that easy with a dedicated cable. So it's not very suitable for a wide area network synchronization. The second I listed here is the GNSS. The GNSS is itself independent of the wide area network connection. But if you want to use and synchronize your sites, you need a line of sight to your GNSS satellites. This is also difficult to realize if you want to synchronize a room inside a building without a window. So you don't have a line of sight to the GNSS satellites and you cannot synchronize your device. The next 2 solutions I proposed here are only IP-based. IP-based is in that case a good thing, because nearly every wide area network supports IP traffic. I listed here the network time protocol and the IEEE 1588 precision time protocol, PTP. The main difference between these 2 protocols is that PTP provides a lot more accuracy than the NTP. So these 2 tools are suitable for our wide area network synchronization. There are also other synchronization protocols like the synchronous Ethernet, SYNC-E, or the White Rabbit, a combination of synchronous Ethernet and PTP. But for the synchronous Ethernet, there is a wire in one Ethernet cable used to perform on frequency synchronization. That therefore you need special hardware to achieve this frequency synchronization. So not usually a wide area network does not have this special hardware and it's not realizable over every one wireless wide area network. So if you apply our LIPS condition, like we have an unknown network that you only want IP, and you want to achieve accuracy of below 1 millisecond, the PTP is a good solution for our synchronization over the wide area network. In our measurement setup, we use the PTP for Linux, and one feature of this protocol is, of course, as I mentioned before, is only IP. The static error can be handled by an implementation for the latency measurement and correction, and also there is an asymmetry correction if needed implemented there. The dynamic error can be overcome by an implemented jitter handling. For example, there are some filters implemented. There's an PI controller and a linear regression algorithm for smoothing out the jitter. The problem here is the pseudo-static error. That is not in detail implemented there. It's more dependent on the parameter you managed for the static and dynamic error handling. But in our case, that we use the pseudo-static errors does not have much impact on our synchronization. That's why I will not go deeper into that topic. Then we had here built up a laboratory test just for testing the performance of the PTP. We built up a PTP master and a PTP client and connect them through our network emulator. With the network emulator, we introduced a dynamic error in form of a Gaussian distributed jitter with a standard deviation of 8 milliseconds. On the right side, you see the result for the synchronization with the PTP algorithm used with the linear regression. On the x-axis, it's plotted the time offset of the client from the master here in milliseconds, and on the y-axis, you see the probability of each time offset measurement. The measurements are Gaussian distributed, like the introduced latency jitter from the network emulator. But as you see, the standard deviation is significantly reduced in comparison to our introduced dynamic error. The red lines in the plot demonstrate the 99.7 percentile. That means that 99.7 measurements lying in between those two lines. We have here a 99.7 percentile of 5 millisecond offset jitter, and that's a significant reduction from the 24 millisecond percentile latency jitter we introduced with the network emulator. Of course, that's a very bad situation for a network. We also implemented this PTP algorithm with the linear regression on our wide area network between Munich and Hanover. And on the right side, you can here also see the result. Here, the time offset of the client from the master is in microseconds, not like before in milliseconds, but it's also Gaussian distributed. You see here also the red lines that shows you the 99 percentile of all measurements we have done here. The offset jitter of the 99.7 percentile is here only at 9 microseconds. You also can see that the peak of this distribution is not at 0 offset. It is at nearly 28 microseconds. This is caused by a light asymmetry introduced by the wide area network between Munich and Hanover. But we did not correct this because we are way below under our condition of the synchronization of 1 millisecond. So overall, we can say that we had a distance between two cities, Munich and Hanover, of around 500 kilometers. And through this wide area network, we achieved a synchronization of below 1 millisecond with our precision time protocol algorithm with the linear regression. So thank you for your attention. I'm open for question now.
Thank you, Heiko. Give me a short minute to look for some questions. There are none at the moment. So maybe Heiko, can you tell me what kind of synchronization method you used in the lib setup? We will see later.
In the lib setup, we use the GPS synchronization method. That's just because we need for our test results with the precision time protocol reference, so that we can ensure that the precision time protocol performs the right way. And that's why we put some antennas out of the window of each room, and then we share, of course, the better synchronization to the other devices.
Okay, thank you for clarification. No other questions. So we move on with our next speaker. It's Alexander. Alex, are you here? Alexander Beifus.
I'm here. Hello.
Sennheiser Streaming Technologies. Hello. Okay, so go ahead.
Yes. Hello. So my name is Alexander Beifus, and I'm working for Sennheiser Streaming Technologies. And the topic of this talk is about live audience services and how we can distribute them in massive audience events. So let's start with a classical audio distribution, like I see it. If we are on a live location, of course, we have some content, which might be a speaker, or in the case of Lips, we have the remote side, where we get content over the wide area network. This typically goes to something like a production, where the audio is mixed, and then it's forwarded to the PA, so that the audience can hear it. The vision that we have is that we hook up a mobile core network or a mobile network so that we can also stream from the production through the core network over radio to the audience, where some of the audience has their mobile phone and headphones, so then they can receive this audio streams over their phones. And this gives us the opportunity not only to have the speaker or the content that comes from the remote side, but also offer other services like commentators or translators, which then can augment the situation there. Okay, let's look at the use cases and the challenges that we see there. Use cases are, for example, at concerts and festivals where we stream the live or the content of the actor, singer through the phones. This might be helpful if this is a larger area and the PA is a bit away, so you can't hear it directly. Then you might want to stream it to your phone. At conferences and fairs, we might use something like translation, for example. And for sports events, we could think of that we have commentators that directly stream through the phone. And the challenges on all these cases is that we have many users which actually require the same data. And for some of the use cases, we have some latency restrictions. So, for example, if we have a speaker or a singer, then we might be lip sync, which means we should be in the range of 50 milliseconds or less. And then there are relaxed situations, for example, with a commentator or a translator, where we have something. It would be nice to have something like 200 milliseconds, but of course it could be larger depending on the actual situation. So let's first look at unicast. I want to show that this is not an option. The problem with unicast is that the throughput that we produce increases linearly with the number of users. And since we are living in a real world, there's a upper limit called capacity. And once we reach this, the whole system might collapse. And so we have actually a limited number of users that we can reach with unicast. Also, unicast means that each client will receive or perceive a different latency. And so the alternative is a broadcast, where we really only send the data once and everybody is listening. So this makes sure that we have a constant throughput on the net, and that each client will experience the same network latency. Downside here is that we don't have retransmissions, so we must use techniques like forward error correction or packet loss concealment or something like this to make sure that a client who who doesn't get a packet properly still gets some audio data and not hearing a glitch or something like this. Okay, how is it in the real world setup? So when we look at mobile networks, what we would see right now is deployed is called a multimedia broadcast single frequency network. And this works the way that we have multiple cells that we synchronize so that they can coordinate their broadcasts. They send the same data actually at the same time and at the same frequency. And this has some positive effects if we have multiple cells, because we can create larger environments. This might be helpful if we have events like the Tour de France, where the area of the event is quite large. And another benefit of this setup is that this improves the reception, because since every cell is sending the same information, these interfere, and this gives a positive gain because we actually receive the data from several cells at the same time. And the reception at the cell edge is better because we don't interfere with cells that send other data. We've got such a setup in our lab, and Georg already mentioned this. And yeah, we don't have many cells there. We only have one cell, and this cell is actually a LTE core network. We have some additional servers in there because broadcasting in LTE is optional. And we got a Nokia base station there from release 9. And of course, we have a mobile phone which can receive broadcast. And this is actually a pain point with the broadcast system in the LTE network. These kind of devices are rare. Okay, how does it work? So we need a structure that a common structure for the UE, the phone, and the base station, so that they know when they receive what kind of data. This structure is called a radio frame, and this is 10 milliseconds in time, and it consists of 10 subframes, each a millisecond long. And yeah, since the structure of the subframes for broadcast and unicast differ, we have to make a decision when we send broadcast and when we send unicast data. And this happens in a time multiplexed way. And since the radio frame has some restrictions for synchronization, so actually subframe 0, 4, 5, and 9 are not available for broadcasting because they carry some synchronization information and paging information. This means we can only use 6 out of these 10 frames, which means with eMBMS, which is the broadcast technique in LTE, we can only have 60% capacity for broadcast. With release 14 and 16, we have further developed version of this eMBMS system. So this is where the F comes from. And yeah, this allows to have a special mode where we can increase the capacity up to 100% if needed. Okay, then next topic I would like to look at it is how we broadcast or how we schedule the broadcast traffic. And this is really important because we figured out that this introduces a lot of latency. So for release 9, this is LTE. The minimum period which we can set for the scheduler is 80 milliseconds. And this means, as you can see here in the figure down below, that if we have a typical pattern of audio frames that we send with frequent timing, then we could have latencies up to these 80 milliseconds in best case. In worst case, it can even be larger. So with release 12, there was an extension, which means we could decrease this to 40 milliseconds. And with release 14, there's the option to have this 10 milliseconds. But this is optional. It doesn't mean that this must be implemented later. Okay, and when we look at some latency measurements in the network, these were done with a a software-defined radio where we set the scheduling period to 320 milliseconds, we can see that we have actually these triangles, or rather a sawtooth pattern that's really common if we have two different systems which run at different rates. So high rate audio, low rate scheduling. This gives this pattern, and we can see we get latencies up to 320 milliseconds there. Here's a real-world measurement for end-to-end audio latency that we did in our lab setup. And what we can see here, the orange line we see is for a scheduling period of 160 milliseconds. And when we drop this down to 80 milliseconds, we can actually really see that this affects directly the end-to-end latency. Okay, and yeah, now what's coming next? So far we've seen what's the current deployment state, and with release 14, there was this new further developed eMBMS system, which gives the opportunity to have a receive-only mode, which is quite important because when we have a live event, maybe there are devices that don't have a SIM card or they're not subscribed and they want to receive these services. Then the frame structure changed a little bit, so the single frequency areas, they can be larger, and I already mentioned that we can get more capacity for multicast. And another nice feature is that operators can cooperate and use a common carrier for broadcasting. And then there is another technique which is not directly related to these MBMS services, but it's doing broadcast, and it's called single carrier point to multi-point. But I don't want to speak about this because the next talk will give a bit more insight on this. That's it. Thank you.
Okay, thank you, Alex. Very nice topic. So we have a question coming in at the moment. Maybe we give it a little time. You talked about mobile networks primarily. Can
Sorry?
you talked about mobile networks primarily? What about Wi-Fi?
Yeah, actually, Wi-Fi could be an option, but there are some points which are not so nice regarding Wi-Fi and broadcasting, multicasting. First, of course, Wi-Fi uses unlicensed bands. This means we might have to cope with other access points nearby. Maybe a guy in the audience set up his own access point. I don't know why. Maybe he's streaming something. I heard that this is common, that people do this. This would reduce the reliability of the net because this access point would interfere with, or could interfere with, the distribution network. Next point is multicast also has a scheduling mechanism, and this and the latency that you get with this mechanism is much higher. Typically it's 300 milliseconds. You can reduce it, but it's not guaranteed that this will work with all the clients. And yeah, and of course, if you deploy a Wi-Fi network, I guess the setup is much more complex to manage, because you need a lot of access points. When we've got a mobile cell, this is quite large, and it's easier to manage. Yeah.
Okay. Well, thank you for clarification, Alex. So then we will move on to our next speaker. It's Dennis Wieruch, directly from Berlin. Dennis, are you there? Hello.
Hello, I'm there. Can you hear me?
Yes, I can hear you. You're a little, well, small. No.
Better?
Yes. Thank you for amplifying your volume. Okay. So the stage is yours.
Great. Yeah, thanks a lot for introduction, Jens. Hi, everyone. I am Dennis Biro, and I'm a research associate at Fraunhofer and Heinrich Hertz Institute, as it's written on there, in the Department of Wireless Communications and Networks. Our department performs research on 5G and beyond, so researching new communication schemes for future wireless communication. This talk will be two-parted. I mean, first, I will jump on the multicast topic, what Alex presented in his recent talk. But there I will talk, as he pointed out, about a promising alternative mode called single-cell point-to-multipoint for massive audience events. After this, then I will move over to opportunities of private networks. This work was, of course, a joint effort of my colleagues here, Jonathan Smith and Martin Kasparek. So on the right side, you can see a concert, which we hope to see again beyond the COVID-19 times. So as Alex pointed out, classic unicast connection is not scalable for large audience. However, wireless multicast is an efficient way to address the large audience. So for large rooms is with multiple transmitting base station, the discussed or presented by Alex, also called MBMS, Multimedia Broadcast Multicast Service, offer semi-static coverage over wide areas. So therefore, it's really beneficial. But for local deployments with a single transmitting base station, the now presented single-cell point-to-multipoint may be more beneficial, offering more flexibility and a latency-optimized communication. So now I will give some details on single-cell point-to-multipoint. A major visible difference to MBMS, which was presented before, is that SCPTM, so that's the single-cell point-to-multipoint mode, can have mixed transmission. That means we can have a joint transmission of multicast and unicast data within each subframe, not as pointed out before that they have to be separated. On the right, you can see the basics of SCPTM. A base station transmits a continuous stream of radio frames consisting of 10 subframes. So in contrast to MBMS, each subframe can be loaded with unicast and multicast data. Thus, we can serve unicast and single-cell point-to-multipoint users simultaneously. So in this way, this scheme has multiple advantages. It enables low latency transmission like in unicast, offers flexible unicast multicast communication, and benefits also from the advances in unicast standardization, because unicast is fully standardized and goes on, and since SCPTM is hardly relying on it, it can benefit from it. However, for large regions, if the multicast shall be present among multiple cells, single-cell point-to-multipoint cannot be deployed like MBMS. They are similar to unicast. Each base station serves an independent SCPTM signal in itself. This you can see visualized on the right bottom. There, a base station is transmitting an independent signal, so the SCPTM signal, in each cell, where the different cells are depicted by the hexagonal colored shapes. We implemented the SCPTM mode and deployed it in our lab. In particular, we extended the open source software called SAS LTE by the single-cell point-to-multipoint mode. And there, as you can see on the right side, we have a mixing console application, which is connected to a base station. The audio stream is routed through the mixing console and transmitted via the base station as an SCPTM signal. So then we have two wireless speakers which are receiving the audio stream via the single-cell point-to-multipoint signal. The wireless equipment, the base station, and the wireless parts of the speakers are based on software-defined radio. In particular, we have an Intel NUC PC for signal processing and USRPs for analog signal transmission and reception. Eventually, both speakers replace the audio stream. So multicast by SCPTM offers a nice alternative to MBMS, and especially using unicast. In summary, wireless multicast is an efficient way to address large audience. However, an open question is how to efficiently get feedback about reception quality from large audience. This also pointed out already by Alex in his previous talk, that if you have broadcast, it's not it's an open question how to make it efficiently that all users can somehow report some states back. Maybe not on a critical time basis, but on a longer time basis. In future, we want to take a look into it. An example is visualized here, where the large audience sends a feedback in a specific way, so that at the base station, we can see a distribution of the present signal quality. In particular, we can see the number of users over the multicast reception quality of the audience down here. So next slides. So to have a successful live audience service, we require professional audio video production in a controlled environment. So this demands for controlled wireless communication. That means we want to have dedicated private access, full control on quality of service, like latency, reliability, and data rate, and flexible deployment anywhere. A promising solution is local licensed spectrum for private access. Last year, maybe some of you are also here, 100 megahertz of spectrum in 3.7 to 3.8 gigahertz has been allocated for this purpose in Germany. Other countries are already following this example, allocating extra spectrum for private access. However, currently the spectrum can be used just for internal access only. To get a license for the private spectrum band, an application has to be submitted to the Bundesnetzagentur. Unfortunately, currently the spectrum can be just licensed for fixed locations only. So, opportunities for the future are to have temporal licenses for live events, as here for example, and access of private spectrum also for the public audience. These options, these open issues have to be addressed and discussed. So now I will present shortly the concept of private networks. As a baseline, we have the public network, which is mostly in a network like you use with your mobile phones. Thus, professional audio and video production services are sharing their communication link with the public. Furthermore, the available communication features depend on the operator, and higher quality of service requirements may be available through network slicing, a special mode in the communication. The hybrid network separates the access between public and professional audio and video production. That means professional audio video production has private access on the private spectrum band between 3.7 to 3.8 gigahertz. Therefore, professional audio video production has dedicated resources and private access. However, features still depend on the operator, and higher quality of service requirements may be available still through network slicing. Now we come to the private network. In the private network, which is also sometimes referred to as campus network, only professional audio video production is present and can access the private spectrum. Therefore, like the hybrid network, professional audio video production has dedicated resources and private access. However, in contrast to public and private networks, the private network has a local dedicated network. Therefore, the features depend only on the available hardware and software. And we expect an increase of diversity of the hardware and software, which is available on the market. Furthermore, since we have a local network, we have full control on quality of service. So professional audio and video production has all capabilities to perform an exciting live event. In cooperation with Smart Mobile Labs, we set up a local private network. The lab setup of the local private network was done with 5G hardware, consisting of a 5G standalone core, which is shown up in the picture, and a 5G access unit, which gives this a white box on there. This local private network operated within the spectrum band of 3.7 to 3.8 gigahertz. There, we used a 5G mobile phone to attach to the local private network, which was able to access the internet over the private spectrum band. So, private networks are already deployable now. This concludes my talk. I thank you for your attention, and you can find further information also on the website below. And I'm happy to answer some questions, Jens.
Yes, thank you, Dennis. So far, there are. Oh, your last slide is black.
Yeah.
Yeah, perfect.
Wrong
So far,
click.
there are no incoming questions, but I have one for you. Private networks and local license spectrum is a huge topic, especially in Germany, since we are the first, I think, who had a license there. Can you tell us how developed this technology is and when it is broadly available for building your own network?
Yeah, it's a good question. I mean, right now, as I pointed out, at first you have to, of course, get the spectrum there that you can, which you can access privately. And of course, because it's in Germany, there is already a lot of deployments going on. I mean, there's, for example, I know of Lufthansa Technik. They rolled out also already a private network, which is operating in this band. But this year, I would say there are a lot of initial deployments to try out the new private spectrum with the hardware. But I expect that in the next year, there will be more and more hardware available and also software which actually can deploy this private network. And maybe as a side note, it's right now it's also that this network will only be available with 5G technology. So that means that all the hardware, as pointed out here also, the core, the network, the access, and the mobile phones have to be able to perform 5G.
Okay, thank you, Dennis, for this clarification. So far, I see no more questions. And okay, then again, thanks, Dennis.
Thank you too.
We will now take a break until 12 p.m. noon, where we will continue our session and we'll start with our live concert. So you have the opportunity to eat something, and we will see each other again at 12 noon. Hello and welcome back to the LIPS final workshop. Now it's time for our session with a live concert. And we will start the session with a short video from one of our project members, TVN. They are a PMSE user and on the forefront of production. You may not know, but they do a lot production in the TV space. So let's play the tape.
Hello, my name is Markus Osters and I'm the Managing Director of the TVN Group. TVN is headquartered in Hanover, Germany and is working with its subsidiaries in different fields of business like corporate communication, ENG crews, post-production, outside broadcast and TV formats. The subsidiary TVN Mobile Production is one of the partners in the LIPS consortium. Today, TVN Mobile Production is a classic outside broadcast company. In the next few minutes, I will talk about how we work today and what will change in our opinion in the next future. After that, my colleague Laura Sänger will talk in more detail about newest innovation in virtual reality and its impact on immersive productions. Within TVN Mobile Production, we focus on premium outside broadcast productions, for example, the German Bundesliga, the international matches of the German national soccer team, Champions League, Europe League for different customers. Furthermore, we realize big festivals like Wacken Open Air and individual concerts, and premium events like Chio in Aachen or the Berlin Marathon. For this, we rely on state-of-the-art OB vans with high-quality technology and a large number of broadcast specialists who travel to the production site and realize the projects. All these resources are limited. Outside broadcast vans are not available in unlimited numbers and are expensive, and there's a shortage of skilled workers in our industry. It is therefore important to manage these resources intelligently and to take advantage of new opportunities. The conditions currently shaped by the worldwide COVID-19 pandemic have shown us at a stroke how vulnerable our business is. Productions have been almost completely cancelled at short notice. Travel to production sites is only possible to a very limited extent. In the meantime, productions have restarted, especially in soccer, but it's subject to numerous additional regulations, for example, in the area of hygiene measures. This situation has given an enormous push to new forms of productions that are better suited for such conditions. Especially the topic of remote productions has been established faster than expected just a few months ago. As a future topic, remote productions has been discussed for several years, especially under cost aspects. There were many pros and cons in the debate about which costs go down, which go up, which infrastructure is needed, how to take people on this journey, etc., etc. This discussion ended with the outbreak of the corona crisis, because suddenly in many areas, remote productions were the only way to produce at all. The characteristics in the countries were very different. In the UK, BT Sports was on the road with very decentralized approaches, in which control rooms, slow motion facilities, etc. were separated from each other and sometimes even operated from home. In other countries, centralized services and the classic remote concepts were realized in order to be able to use core technologies several times and reduce travel activities. BT Sports now advertises with virtual and augmented reality over 5G. That's how fast development is there. Germany is probably the country where the least has happened in relative terms. Firstly, because the necessary infrastructure, such as fiber connections or even 5G networks, are not available to the necessary extent. Secondly, because hygiene concepts were developed in a very early stage, primarily by the DFL, which allowed an early return to classic production concepts. This meant that there was no need to establish remote production concepts at short notice and high numbers. Nevertheless, the topic of remote production has established itself in the last few months, as an incredible amount could be tried out under live conditions. Quality, especially in soccer, was no longer the dominating topic, but rather to do productions at all. Even though we are not yet ready in Germany as far as infrastructure is concerned, remote productions will increase and establish themselves in many areas. The infrastructure is getting better, 5G is being expanded, consistent IP workflows get more and more established, and so on. The future is becoming more complex. Remote productions will be a further addition to production concepts. There is no one-size-fits-all. We are working intensively on this topic and have developed various production concepts. From our point of view, the cost aspect is not necessarily the most important. In order to achieve relevant cost savings, many basic conditions must be right. But remote productions will make new things possible. If the technical basics like latencies, connectivity, etc. are right. Suddenly, for example, multi-location remote productions can bring together people who otherwise could not meet to create music together. On a small scale, this could be a band rehearsal with the band members in different locations, but also 2 big festivals brought together virtually. Also, new formats will emerge that allow new ways of participation and exchange between city and country in the fields of culture and politics, and much more. In order for us as a user to be able to realize this, the results of the LIPS project will help us to design custom-fit solutions. In order to create a common feeling in different places, as many senses as possible must be addressed. This is about lighting mood, video settings, new possibilities like 3D audio, and all this with as little latency as possible to create a truly immersive experience. The cooperation with our partners at LIPS has enabled us to look at this topic from a different perspective and to better judge what will be possible in the near future. Especially the current situation has shown how important such approaches can be in order to make culture, politics, and sports not only an experience, but also to enable real participation and interaction. The future will not be only more complex, but also, at least in part, immersive. We are looking forward to this.
Hello, my name is Laura Sänger and I'm leading the Department of 360-degree Video and Virtual Reality at the TVN Group in Hanover. I want to tell you where we currently stand when it comes to immersive media and take a look on the future development in this area. Since 4 years in our department, we focus on 360-degree video and virtual reality productions. We do everything starting with concepts, storytelling, the production as well, and post-production, of course. We luckily had the chance to produce manifold projects in different fields of application. So, for example, you can see we do 360-degree live streaming for the telecom, we produce full-dome film production as well, and we produce 360-degree content, for example, for the ECB. So, one of the main questions I always worked on was, how can we use immersive media for reasonable and for sustainable solutions that can make a difference in the varied fields of education, environment, and science? How can we use immersive media to transmit messages beyond just nice games or entertainment? And how can we achieve to bring the user in touch with the content? So at first we should take a look on what immersive media actually is. Immersion means the sensation of totally dive into another world. So that is the main reason why I absolutely love this medium, because it turns upside down our perception and everything we learned about storytelling and composition. So immersive media can be VR or 360-degree video, where you totally dive into a digital world that shuts down the real world. Here, for example, we fly on a hot air balloon using VR lenses. Or it can also be AR, where you combine digital content on top of your real world. So there could, for example, appear a real seal in your exhibition. There now exists various VR headsets, and since we don't need a mobile phone to plug in our VR lenses, the usability and the number of users has risen much further to establish immersive media as one of the most important media influences right now. And that is what prognosis tell us as well. Till 2021, we expect 19 billion US dollar turnover with virtual reality worldwide. And the user amount will rise up to 24.4 millions. So, of course, there also exist various 360-degree cameras that allow high-quality film productions, from action underwater so that you feel like a whale, for example, or 360-degree drones that make you fly like an eagle through the air. But what all these technique helps to produce is one essential phenomenon, the immersion, the feeling of actually being in that other space. So instead of watching a movie about a hot air balloon ride, you now really feel like being 400 feet over the ground, having maybe some strange things happening in your stomach because of the hikes. So immersive media affects differently our body. It can affect our stomach or our body in general. So in other words, it touches you physically and in that way involves you more emotionally. And that's why immersive media is so fascinating to me, because it reaches our audience in the most intensive and sustainably way. And as we all know, we all learn the best by active and cooperate learning, which ensures a lasting effect. So because of its useful effects, one of the most important fields of application is definitely education. So in this context, I would like to present you some of our latest projects at TVN. We developed an interactive application in 360-degree where you can prove your first aid skills and save the protagonist's life. Applying all the steps you learned before in VR, that helps immensely to remember everything much more sustainably. There's another interactive VR app we made in cooperation with the European Union. It's called EU Beam Me Up and VR Europe Let's Vote. It explains in a very playful way how the EU works, and they encourage young people to vote. Answering a few questions, the user can decide the storyline and meanwhile approve his knowledge. So the app is the perfect addition to political classes at schools, and it is right now used in several European schools in Germany. So I like that project very much because it shows how VR can be applied in a very useful way. And that brings me to our actual project we are working on, an interactive exposition in the Erlebniszentrum Naturgewalt in Sylt, which is about the climate change and our social responsibility. We used, for example, AR to bring to life typical animals from the island. Or there is a VR paraglider where you get to know the island from a very new perspective. So, in my opinion, immersive media is one of the most influencing media trends right now, because it has the potential to embrace people, to encourage them, and to change their consciousness. And doing so, it appropriates digitalization in the best way. So one of our main business segments is, of course, 360-degree live streaming. We are producing all the festivals for Magenta Musik. So it is important that we find new solutions as well in 360 live streaming to manage, for example, high data rates, using 5G technology, and to include 3D audio as a massive component of immersion. This will bring new changes to develop totally different scenarios of, for example, remote learning, of sharing emotions, entertainment, and finally, more immersion. So let's go on researching in more projects like LIPS, so that immersion can be used in more fields of application, because it is absolutely clear that science, education, and economy will totally benefit from it. Thank you very much.
Thank you, TVN, for these insights. It seems to me that immersion is a very hot topic, and we'd like to give all our viewers the opportunity to be immersed by our concert. But first, we hand over to Norbert Werner from Sennheiser to give us a little introduction of what is about to happen. Norbert, hi.
Jens. Yeah, thank you. My name is Norbert Werner from the Research and Innovation Department here at Sennheiser. And in the next few minutes, I will give you the introduction to the highlight of today's workshop. We have prepared a live concert with 5 musicians at 2 different locations for you, live, not pre-recorded, and we will stream it to your home. So first, the basic setup of our streaming demonstration system. We have one part of the stage in Munich, inside of the Music Academy, where a bass player and a grand piano player is performing for you. And the other part of the musicians is located 500 kilometers more north in Wedemark, near Hanover, inside the Sennheiser headquarters. There we will have a drum player, guitar player, and keyboards. To enable this performance, we use a dedicated wide area network with a capacity of 1 gigabit per second per direction. And over that network, we are able to transmit 6 separate audio links from each direction to the other, and 1 video stream. Additionally, we will have some lighting control information on that line. Since the setup is more or less similar on both sides, I will exemplarily explain to you the setup a little bit more in detail for the Wedemark side. Here you can see the 3 music instruments representing the 3 musicians. All these music signals are captured and transmitted to an audio mixing desk. The same is happening on the Munich side at the same time, and these signals are transmitted over the wide area network you see on the left side via the audio gateway to the same mixing console here in Hanover. From all these audio signals, we create individual audio mixing for the in-ear monitoring systems for the 3 musicians. That the musicians are not only able to hear each other and perform together, but also can see each other, we use a network-enabled camera, recording the whole scene and transmitting it to Munich. The video signal from Munich is transmitted back to Hanover and is shown on a screen that they can see each other. To adapt the lighting situation on both sides, we have controllable lights and spectrometers for analyzing the setup, interconnected by a lighting gateway described in a prior presentation. To support the music performance, we also have in place a global metronome that can give acoustic and optical click signals to the musicians to support them. And to keep audio and video on both sides in sync, we installed a time synchronization service based on GPS signal, so it gets the current daytime from satellite and distributes it over precision time protocol in the local network. Now let's come to the real life setup. Here we see photographs of the setup. On the left side, you see a picture of the Munich part of the stage, where the grand piano and the bass player are sitting. And you can see there's a television where they can see over the LIPS system the musicians performing in Hanover. Same the other way around, you can see on the right side the musicians performing in Hanover, seeing the musicians in Munich on the television. The whole scene will be recorded from outside with separate cameras and distributed to you via standard web streaming technology that you can see it in this workshop. Over the same system, we will perform a podium discussion after the concert. And now I will hand over to Klaus Stratzicki, the vice head of the recording studio of the Music Academy in Munich. If he's still there. Maybe we have some technical issues here, or not everyone in place right now. So now we are there. I saw a video signal. There you see the location in Munich, in the Music Academy, the musicians performing. And Klaus, the stage is yours.
Music and Performing Arts in Munich. I work here as an engineer and teacher. And first of all, a warm welcome to all of us to our university and to our little performance for the LIPS project. I would like to introduce the two musicians here. First on the piano we have Victor Ardelian, and on the bass we have Hans Königke. They are both composers in our study course, Composition for Film and Media here in our university. I can see that something is already happening in Hanover. I would like to hand over to Dr. Raphael Töne, who is taking care about everything which is happening in Hanover. Hi, can you hear me, Raphael? No? It looks like he's not.
Hello, hi.
What I said.
Can you hear me? Okay.
Yeah,
it's my pleasure to welcome everybody here in that room at Wedemark site, and we are proud to be a part of that project as the Hochschule für Musik, Theater und Medien. And first of all, I'd like to present or introduce the band. We are getting the band together like Blues Brothers. So on guitar we have Julian Scacella. On drums it's mein Gott, Max Dost and Lukas Blex on synths and keyboards. And it's a very challenging and interesting project, and I'm looking forward to hear the comments that you will share with us later, and I wish everybody in that project good luck and enjoy.
hallo, kann man mich sehen? Ich habe leider kein Feedback-Bild mehr. Deswegen, ja, ich bin total geflasht. Danke auf jeden Fall, danke auch nach München, euch beiden. Ja, wir würden jetzt gerne eine Panel-Discussion mit euch machen. Ich muss mich erstmal sortieren. Vielleicht ein kleiner Anmerkung. Hier im Raum hört man eigentlich nur das Schlagzeug. Als Zuschauer ist es ein bisschen merkwürdig. So ein bisschen wie Phantommusik für mich. Und ja, ihr Musiker hattet wahrscheinlich ein anderes Signal auf den Ohren. Max, vielleicht fangen wir einfach mit dir an. Du bist derjenige, der die Percussion gemacht hat. Warum habe ich eigentlich jetzt auf Deutsch? Sorry, okay, I will switch to English now. Okay, Max,
right.
you did the beats,
Yes.
which is very important for keeping synchronous, also to the musicians in Munich. How is it that it's very loud in this room? Does it work for you and the other musicians, or what are your impressions?
Yeah, for me it worked quite well because yeah, all other musicians has to follow me and I have to follow nobody. That's yeah, very good for me in this situation. Yeah, but I was very surprised at the start of this project how good we could interact between Munich and Hanover because I was a little frightened at the start that the latency, I don't know, latency, okay, that the latency would be too harsh to us, but yeah, it worked out very well. Yeah, and I guess we made some good music, I hope, so.
Well, unfortunately, I couldn't listen to it. But other people here in the room had the in-ear monitor, and as you guys had. So maybe one question to the musicians in Munich. As Max already mentioned, in the preparation for this concert, you practiced a lot together. And for discussion and coordination, you guys had also this visual link. It's like a window in the other room. How did it feel for you to have this window in the other room? Maybe Victor, you can answer.
Well, of course, it helps a lot to see the musicians in a big screen in high quality. It almost feels like they're actually just a few meters behind the screen. Unfortunately, the latency of the image is not exactly the same than that of the audio, so sometimes the synchronization wasn't perfect, but this was actually minimal, and it's very realistic to see them playing what you actually hear. For us musicians, it's actually the audio, the most important part, that we are together in time, and that works very, very well. We could hear each other, and that also makes this virtual environment 99% realistic, I have to say.
Okay, thank you for that. Maybe we come to a different topic or other side of this whole project when it comes to teaching, and I would ask Dr. Töne, when it comes to teaching music, what is the current state in digital online participation, and is the setup an option for remote learning and cooperation with artists all around the globe?
I mean, at any music institution or academy, we were very heavily hit by the pandemic, and we had to reorganize all our schedule, and we used several different video conference tools. So I would say actually we got used to use that new medium, and state of the art is probably that you can combine prepared slides with PowerPoint, you can interact with notation software in online examination and classroom situation, but this is actually the real step, I believe, that will be what we can further work on in the future, because you can use, there are some solutions on the market, but I mean, in terms of latency, they were pretty bad, and it's astonishing to realize that you can really interact and play together with other musicians over 600 kilometers away. And I was also impressed by the point that it's not only interaction, but you can really play with time, and particularly for jazz musicians. I mean, when it comes to the term time and timing, it's something you want to, I mean, a real musician always wants to play with that factor, and that makes that situation so astonishing and so exciting.
Thank you, Dr. Töner. So again, it sounds like latency is the key critical issue here, and our setup achieves very low latency so that the musicians can play together. Maybe also on that topic, a question back to Munich. Maybe Hans, did you use during the lockdown and the corona pandemic special tools like Skype and Zoom for producing music? And what would you say is the difference with this setup?
I think I didn't use Skype or Zoom to produce music because the latency would be too high. So playing music together throughout Skype or Zoom wouldn't work. So I would do it on my own at home and then share the music I produced to somebody with Skype, with Zoom, but not during the working process. So I think this is probably more possible with this Libs project.
Okay, so you're saying the current or state-of-the-art tools we all use during the pandemic are not sufficient enough?
No, not for doing live music.
Thank you for that opinion. And maybe from another side, from a musician, Julian, you are not just a musician, you're also a producer. And the corona pandemic hit us all very hard, especially the arts in particular and the stage artists. Do you think with digital networks performing live music, this is a new distribution channel?
Well, first of all, it depends on the point of view. For the pandemic now, it's good to have solutions, so we still can do our job, playing music for the audience. But still, though, it is sometimes not the same like in real time, because you have to imagine we're sitting now here in front of a camera and playing. Usually you have there the audience. What you are seeing on screen is actually what you see here. We are just sitting in one room playing like in an, let's say, rehearsal or good recording environment. This is always a great starting point. I mean, we always have evolution in music, something will change, and we have new generations who sometimes think this is also great. You have to see the point of view. Older generations, let's say jazz, like Mr. Turner said before, would say and argue, man, this is not the old way. The people cannot react to each other. They see obvious. Some younger generations like me would say it's quite interesting and cool to sit here and play with some people in Munich while, yeah, we are here in Hanover and sometimes you forget it. So it's quite interesting. But we need to a bit time to evolve everything, I would say, because this one is a very great situation, but I'm looking forward what is going to be the next step now here. So I'm sure it's going to be great.
Okay, so the stage is definitely not obsolete, and live music on stage will be part of our culture in the future, and we'll probably adjust this digital channel to the distribution. Okay, maybe the last, Lucas, question for you. I almost forgot that Munich is 500 kilometers away. What was your feeling? Were you aware that the other musicians are that far away and not in the room next to you?
No, definitely not. They could have been next door because doesn't feel like we had that much latency, which you would expect by 600 kilometers. So they could have been next door.
Okay.
In my opinion.
Thank you. Yeah, I think that's all from our side. And I will do a short wrap up now, and then we will close our transmission or broadcast. So we learned a lot about the Libs project today. We had certainly very in-depth technical talks in the beginning. And after a break, we had this, well, really, really nice concert. And again, thank you all, the musicians, for performing, for the rehearsal sessions you did. And thank you, Munich, for the technical assistance. And thank you, Sennheiser, and all the partners. And I will say goodbye now. Take care and stay healthy.
Hey Hans, Victor, war schön euch kennenzulernen. Na, bleibt mal weiter.
Niemand ist mehr auf Facebook.
Ciao, danke euch allen.
Ciao.
Und wenn ihr in München seid, kommt auf